only PV.
Only PV work. Only PV work. That's what it means.
I thought it meant excluding PV work, as in the function itself is only delta U.
But you're restricted to using only PV work.
Yeah.
PV work is what they call the natural work of a chemical reaction if it's done under constant pressure.
Yeah, I know what problem with that is, but depending on if it excluded it or limited it, changes the answer completely.
Well, actually, you could pick any work. If you restrict it to any work, it will turn into a state function. It just that would be the best to do. But anyway, I know I had a question about this. Tomorrow is the last day to drop, and so what I'm going to do is I'm going to try to get the exams graded and the scores into tomorrow. If you have any questions, you can email me as well.
Can I ask a question about one of the exams?
Yeah.
What was the answer before?
44. Remind me what the question.
I can write it down.
You don't have to write it down. Just tell me what it was.
With a 50 milliliter of 1.05 molar sodium hydroxide plus 75 milliliters.
Okay, yeah, I know.
1.6 molar hydrogen chloride at 22.3 degrees Celsius for both. Whereas the final temperature of the density is 1.02 with a specific heat of 3.83 and a delta H of, I believe, negative 55.6 kilojoules.
All right. That problem?
Yeah.
There's a question about that one?
44, yeah.
Okay. What was the answer?
I got way too high of a number. But
yeah.
I got,
T final?
let's see, for T final, I got 1,088 degrees Celsius.
1,088 degrees Celsius.
I thought that was a little high.
Oh, that's a bit hot.
I might have gotten that. I'll just
Did
say
you
I did.
know?
But I don't know where I went wrong either.
Was it 28?
Actually, I need to double check that. Let me double check it, but that sounds reasonable.
Why did it somewhere in 34 something?
34.
Something. Seems like a reason.
Yeah.
If you get it something over, let's say over 100, then what's going to happen is it's going to peak out at 100, and then the rest of the energy is going to go into boiling the water, so we'll go into the process. But that doesn't come until chapter 12 or something like that.
I kind of figured that.
But 28, anybody else? 34, 1,000.
What are you talking about? Go big or
I
go
think
home?
1,000 is a bit too high. But yeah. Yeah, but 28 seems reasonable. I mean, we could do it, but do you want me to do it or no? Okay.
I know I got it.
Yeah. Wait, I had another one.
Mm-hmm.
What is it? If gas is compressed and it's an adiabatic process, does it decrease or increase?
Well, if a gas is expanded and you do an adiabatic expansion, what happens to the temperature?
It's expanded.
If it's expanded, temperature decreases, is correct, because work is being done. System expands, work is being done. So energy is conserved. So if it costs this much energy to expand, then you get that much energy back if you compress it. So it actually heats. So compressing gases, maybe I talked about this briefly about like if you pump a bike tire pump or something like that, it starts to get hot. Have you noticed that? Uh-huh.
So it would be that, like when a balloon inflates, right? Like the volume increases and would the pressure then decrease then, or would it stay the same? So then,
The pressure would stay the same. The pressure wouldn't change. It's like the it's like the compressed air cans or compressed gas cans that people use to spray off.
When it compresses, it gets colder, but isn't it abiotic?
When it expands, when you release the gas out of the can, then it gets cold.
But the reaction is abiotic because it's not transferring any energy to the surroundings.
Right, and so the work that's done has to come from.
from the system itself, which means it uses energy.
Yeah, so that was adiabatic compression, which is would be the opposite of adiabatic expansion.
You got to get iso.
Yeah, if you go up one, let's say you go down, or the opposite.
But you just use PV-nRT for that, right? Just see how they're inversely related.
Well, yeah, it would be inversely related, but it's going to be heat doesn't change. Just
V and T.
Yeah, V and T would change, but you wouldn't use the combined gas cell for this. I mean, I suppose you could.
You kind of see it.
Yeah, you could. You could use the combined gas cell for this as well. But conceptually. Okay, were there other questions? All right, so let's continue on with our discussion. What I want to do is I want to get into chapters 10 and 11 are combined. Chapters 10 and 11 deal with molecules, not just molecules, but compounds, bonding and compounds. And so what we're doing in experiment 8 and 9, experiment 8 and 9 is chapters 10 and 11. But before that, we need to finish chapter 9. Chapter 9 is a fairly short chapter. And so we're talking about size trends. These are the periodic trends. The smallest is going to be helium. The biggest is down here. And then what happens with size is it decreases as we go across the periodic table. That's what we expect.
It decreases from left to right.
Yeah. And it decreases from left to right because what is happening?
Because the proton count's getting bigger, so Z effective is getting.
Yeah, Z effective is increasing. Yeah.
Which means that you're getting closer to the end.
Right. And as we go left to right, it's same shell. So we're adding a same shell electron. So what's happening is Z is increasing by 1. So let's go right one step. If we go right one step, we go +1 in Z. But what happens is we're also adding another electron. So if we add both the proton and electron, the electron should cancel out the positive charge of the proton, but it doesn't. It doesn't cancel out the positive charge because it's going in the same shell. The same shell electrons are very effective shielders. No. And so same shell electrons are not effective shielders. They can shield, but they only shield what percentage about?
33%.
Yeah, something like that. So same shell electrons not effective shielders. However, something interesting happens in this region here. You know, we expect it to decrease across the transition metals, but what happens is we hit the transition metals, it stays fairly constant. You know, there's a small change in the radius. The radius is how we typically measure the size and diameter of the radius. And so let's take a look at this visually. Bring up, there's a nice figure in the book. Bring up here. So basically what happens across the transition metals is the radius doesn't change much. Can you think of a reason why the radius wouldn't change much going across the transition metal? Because Z is increasing. So for each step we take in the periodic table, we're adding a proton, but we're also adding the same shell electron.
Because the radius is the same of that subshell, so it's not going to add any distance.
Okay, the radius is the same for that particular subshell. How about for the P subshell? If we look at the P subshell, once we hit the P subshell, then it'll start decreasing once again. So we hit the P subshell, and then it gets smaller as we go across. So is the radius of the P subshell the same, or is the radius of the P subshell different as we go across P subshell?
In this P subshell.
Within the P subshell, yeah.
Yeah, across the whole P subshell, the radius is the same, I think.
And so then it should stay the same.
Oh, okay. Wait, no, because the positive charge of the nucleus is increasing, but then the distance, like that the electrons can go, is not increasing, which is the valence electron.
Yeah, of course.
Okay, we'll look at, let me just do this. We'll look at a couple of figures here. And so, the first figure is going to be from chapter 9. And that would just be, the atomic radius is something that's kind of tricky to measure because atoms are not hard shell. You know, atoms will have a cloud, a probability cloud, or electron cloud. And so the electron can be within the cloud with 95% probability. So there's no, like, if you were to put a probe here, you wouldn't be knocking on 95% probability boundary because this is just some construct that we made up. And so there's no, like, hard shell. But in a way there is, because if you put a probe, you can't push it too far in because you're going to get repulsion. You know, repulsion to the nucleus, repulsion to electrons. So you're going to start meeting resistance as you try to probe this. Electrons there. And so typically the way atomic radii are measured is you bond it to something. So for example, in sodium metal. So we bond it to something like sodium and sodium here, the sodium metallic bond. And then we can pinpoint the nuclei without a problem. We don't have that Heisenberg. Well, the uncertainty in pinpointing the nuclei is very small. So you can determine with pretty good accuracy and precision where the nucleus is in space. So you can pinpoint the nuclei and then just measure the distance between the two nuclei. That would be called the bond distance. From the bond distance, we just cut it in half. But the thing is, it depends on what it bonds to, because some things it bonds stronger. If it bonds stronger, you know what happens in the bond length? It shrinks. The strong bonds have short bond lengths. Weak bonds have long bond lengths. And so we look. And so, for example, if we made the molecule, this is called the covalent radius here. If we made a diatomic sodium, that is just two sodium atoms, versus having a chunk of sodium metal. If we have a chunk of sodium metal, we see the bond lengths are different. And so what do we call the radius of a sodium atom? What we call the radius of a sodium atom depends on what it's bonded to. And so the radii that we're going to look at are just an average of a whole bunch of different ones. But
A whole bunch of different materials, average of that.
well, it depends on. So, for example, if we're looking at, let's say, the metallic radius, this should be pretty stable because this is metal. But if we're looking at the ionic radius, it depends on what ion we're bonding it to. So, for example, chloride is -1. But if we bond it to an oxide, there could be a stronger attraction there, which would pull the ion even closer, which would mean the radius changes a little bit. And so, based on a lot of different ionic compounds, then there's going to be slight variations here. Then we can get the average. And the average radius for a sodium ion will be the ionic radius. And so we have the atomic radius here of different elements. And it's going to be an average radius of whatever they're looking at, but we can plot it out here. And what we see here is this: as we go across the shell here, as we go across from lithium to fluorine, it gets smaller. It gets smaller because Z effective decreases. If we look at the atomic radius, this is in picometers. So 150 picometers would be
150,000 nanometers.
okay. Well, nano is only three different. Yeah, 150,000 nanos. Actually, the opposite because pico is smaller.
All right.
And so it'd be like 0.15 nanometers. But what we probably want to do is we probably want to use either picometers or angstroms. Do you know how many angstroms that would be?
15.
Not 15. 1.5. 1.5 angstroms. So this is why people prefer picometers, because you don't have to have a decimal. This would be like 1.50 angstroms here. 2.00 angstroms. That's the radius. Then you have to double it for the size of the atom. So what's the biggest atom that you see here? Cesium. Cesium's radius is about what?
I'd say 275 picometers or about 550.
Yeah, okay, and that would make it what diameter?
Big.
It's big, and so it's one of the biggest atoms on the periodic table. How big is it? Like just ballpark, you know, over 5, closer to 6 or closer to 5? Closer to 6. So this is why we say, okay, atoms are about, on the big side, 6 angstroms big, right? Because that would be the biggest. On the small side, we don't have hydrogen here. It's down here, so double it's around 100, 1100 angstroms. And so atoms range from not 100 angstroms, 1 angstrom to about 6 angstroms or 100 picometers. Although 100, you should probably go down to 50. You know? I just don't want to say point. Well, this is fluorine, which is one of the smaller atoms. We'd have to double that, so it'd be around 100 as well. Helium's the smallest. Helium's under 1 angstrom in diameter. And so we have to be careful. Are we talking about the radius or are we talking about the diameter? But take a look. Z effective increases, Z effective increases until we get here. When we get here, the initial, this is potassium, calcium, scandium. When we get to the initial transition elements, it decreases. So it goes scandium, and then titanium, and then vanadium. But look what happens after vanadium. Do you see it? It flattens out. It flattens out. Why is it flattening out?
Metallic bonds.
Why it's flattening out is this. The reason is because of size. When we look at that shell, it's 4s, 3d, 4p. But as we go along the transition metals, you know, the size stays relatively constant here because we do plus 1 proton, and then we do plus 1 electron. But where does that electron go? What orbital does that electron go? Into a 3D. Now, 3D, are they very good shielders? No, you wouldn't say 3D is a very good shielder. However, when we think about the size of the orbital, what are we shielding? What we're shielding is the outermost, because the outermost electron should dictate the size of the atom. And so what is the outermost electron in vanadium?
3Ds.
The 3Ds aren't the outermost. The outermost electron would be the 4s. And so when we look at it here, okay, the 3D are going to be out here, but the 4s are going to be further out. And so what we say is that when we add another proton, we add a core electron. Because it's n equals 3 versus n equals 4. This would be the outer electron. And since shell is all mixed up, you know, when we're talking about shell, the N shell, period shell. What shell are we talking about? I'm just going to call it a core. So for every proton we add in here, we're adding a core electron, which is an inner electron. It's inner because 3d orbitals are a heck of a lot smaller than 4. If we think about the probable distance, just using a hydrogen atom, it's 9 times closer to the nucleus versus a 4, which would be 16 times further from the nucleus. And so it's quite a bit closer to the nucleus. And so these 3D are effective shielders. Effective shielders of the 4s electron. So we have the 3D orbitals are good at shielding the 4s. Although the 4s are more penetrating, so it's all tricky. Versus if we have same shell, for example, over here, once we hit the P, then we aren't going to have that situation. It's going to be in the same shell. So that 3D is going to block that extra proton from the nucleus. So that's the figure. So if you're a 4s electron out here, okay, and then we add another 3D electron, the 3D electron is going to be in this range here, and that's going to block that 4s quite effectively. And so this flattening here of the radius is because of the 3D effective shielders. Do you see the flattening here of the radius? And that's because, well, actually, it's not even flattening. This is really kind of weird. But, as we get bigger and bigger, these effects have issues. So the main one you want to know is here. And then we got these flattenings here because of the shielding. And then the 4F, we have the same issue happening with the 4F over there. And so this is why there's some weird features here. These weird features here we have to investigate further in order to understand. And so that's one of the weird features there. Okay, that's atomic radius. And that's a good figure for atomic radii. In our book, let me show you that. Here. The gold ones are for the atomic. The blue ones are for the ionic. But here you can kind of see it. You see it shrinking, and then flattens. So we're at, where are we at? 134, 128, 127, 126, 125, 124, 128. It's pretty much flat. Then it tops up a little bit and then shrinks down again. And so that's what we want to know. So the overall trend is this. The overall trend is, do you see as you go from left to right, the atoms get smaller, except in the transition metal block where it kind of does that weird thing. All right. The next periodic thing we're going to look at is ionization. What do you think is going to be easier to take an electron from? Rubidium or strontium? Rubidium, why?
Because it's bigger.
It's bigger. Rubidium or potassium? rubidium. Rubidium should be a lot easier to strip an electron off of because it's so big, and the electrons are far away. Which should be the hardest? Yeah, fluorine. Actually, helium. Helium is the hardest. Because it's the smaller. Okay, so size and ionization energy are related to Z effective. And we talked about Z effective, right, Slaters? Do we do that?
Yeah.
We're not actually going to do calculations. You can see what the Z effectives are. The Z effectives are plotted on here. So Z effective for lithium is about 1. And then it increases a little bit, but not by much. Just a little higher than 1, a little higher than 1. So. And the Z effective is about the same, but the electron it's acting on is much further away. And Coulomb's law says that the electrical attraction or repulsion is going to depend on the magnitude of the charge and what? Coulomb's law of magnitude and size. And distance or size, yeah. Now, the way we define ionization energy is IE. We have an atom, and it's going to be in the gas phase. So it's just a single atom. And then you knock off an electron off to make an ion. Also a gas phase ion. The amount of energy this takes is what we call IE1. IE1 is to knock the first electron off. Some things we knock more than one electron off. And so we'll have an IE2, which will form the 2 plus. Actually, plus an electron here. Ultimately, we get 2 electrons there, etc. And so we have IE3, IE4. Depends on how many electrons we knock off. So what we're going to do is we're going to look at the trends in on IE. Obviously, the more electrons you knock off, the harder it's going to be. So IE1 will be the easiest. IE2 is going to be harder, and it's just going to get successfully harder to remove more and more electrons off there. And so we're going to focus on IE1 right now. We're going to look at trends in IE1, ionization energy 1. It's the same as the size. And so which one do you expect to have the biggest ionization energy? Helium. And so this is going to have the biggest IE1. So let's take a look at what those numbers are. So what are the ionization energies?
Would that be not the lowest? Would it be something like cesium or francium?
Yeah. Francium should have the smallest. Yeah. Here's IE1 for our, this we call it EI. There's so many different symbols. But that's whichever. This is a very compact symbol. This is for magnesium. Magnesium likes to form 2 plus. And so we're going to have I1 and I2. Or I'll call it IE1 and IE2. And this is Hess's law. Hess's law works in this. So if I need to knock off 2 electrons, I just add these 2 together. So to ionize 2 electrons on magnesium is going to cost me about over 2,000 kilojoules.
2,189.
Okay, thanks. That much kilojoules. And so we add those up. Actually, that's a lot of kilojoules.
Does it have to be gaseous?
No. It doesn't have to be gaseous, but what they did was they have these 4 gaseous. Now, if it's not gaseous, it's not going to have the exact same energy. It's going to have a different energy for ionization.
So that's like the definition.
Yeah, this is the definition for gas phase. but we'll just use it. And then we can use Hess's law if we want to do a solid. So if we have a solid, the first thing we do is we melt the solid. That's going to cost us energy. Well, actually, the first thing we do is heat the solid as an object. So we're going to do this later. So we heat the solid to its melting point. Well, that's an object heating, Q equals mc delta T. And then we melt the solid. Well, that's a process. So Q is equal to the amount times delta H of fusion. Fusion's for melting. And then we heat the molten liquid to its boiling point. Well, that's an object. Q is equal to mc delta T. Then we boil the liquid and vaporize it. That's a process. Q is equal to the amount times delta H of vaporization. And then we break the bonds. If there are any bonds, Q is equal to the amount times delta H of bond energy, or the bond enthalpies. And then we ionize it. And so if we wanted to do something like that, we have to add all these steps using Hess's law to do it. Because not everything's in the gas phase, and not everything's an atom.
So what has the highest ionization energy? Helium, and it's about 2,500 kilojoules per mole. There's a lot of energy. What has the lowest ionization energy? Francium. Francium's ionization energy is about less than 500 kilojoules per mole.
Actually, it depends. It might be.
Actually, it might be cesium. You're right. Yeah. Oh wow. Yeah. It could be cesium. We would have predicted francium because francium is bigger than cesium, but maybe due to something else. We have to look.
There's too much to give, Francie.
Right.
So big.
Right. And so this is why you remember we have the two-pronged approach? Sometimes the calculations aren't so accurate. And so what we do is we look at the experimental data. Experimental data is fact. And whatever we calculate, or whatever rationalization we use, we have to make sure it agrees with experimental data. And so there's got to be something in addition to size, because francium is bigger than cesium. But for the most part, it goes with size. So cesium here looks to have the lowest ionization energy. It's the easiest to ionize. The hardest to ionize is helium. And so let's take a look as we go across. We'll go to the second period. This is our first period up here. Hydrogen has a fairly high ionization energy as well. Okay, we go to the second period. We start off the second period with lithium. Lithium is the biggest, right? Fluorine, not fluorine. Fluorine's here. What's the smallest? Neon's the smallest. So lithium's the biggest, neon's the smallest. So which one's going to be easier to ionize? The biggest one, lithium, and the hardest to ionize would be the smallest one, neon. And so it just follows the size. Do you see that?
Yeah.
It follows the size except for, you see a couple of blips here?
Yeah.
Sometimes we ignore these blips, but you see the blips repeat here? And so what do those blips do? Two. And so the first blip is going to be lithium to beryllium, beryllium to boron. So all of a sudden, it goes like this. Lithium should be the easiest to ionize, and then beryllium, and then boron should be more difficult, but it turns out boron's easier to ionize. Why? With boron, even though boron's smaller, it's easier to ionize than beryllium.
No.
Okay, what is it?
The valence electrons. Because we're moving from an S shell to a P shell.
Yes. That's the reason why. This is ionizing a 2p electron. This is ionizing a 2s electron. And so s electrons are more penetrating than p electrons. So 2p electrons would be easier to ionize than a 2s electron. And so basically we expect the ionization energy to do this. As we go left to right, the ionization should increase, i.e. 1. And so the ionization energy for lithium should be less than the ionization energy for beryllium. In other words, beryllium should be harder to ionize. Boron should be harder to ionize because it's smaller, but we're ionizing a 2p electron versus 2s. So it doesn't follow the same trend. So this is an exception. But once we're in the p's, then it goes as expected. And so here, this is boron, and then carbon's harder to ionize, right, than the boron because carbon's smaller. So if carbon's smaller, we expect it to be harder to ionize, and it's a 2p, so there's no difference there. And so the ionization energy increases as expected. And then after carbon comes nitrogen. Nitrogen's harder to ionize. Because it's even smaller. And then we get to oxygen, which is even smaller and should be harder to ionize.
But it's easier.
But it's easier to ionize because you see this blip here? Yeah. It's going from nitrogen to oxygen. So why is oxygen easier to ionize when it's smaller? And so this one is also something that doesn't fit our trend. Can you think of a reason why, though?
We're falling out of the 2p subshell.
No, we're still in the 2p subshell.
Right, but now we're starting to pair electrons.
Yes, right. We're starting to pair electrons. The reason why oxygen is easier is because we're removing a paired electron versus an unpaired electron. So oxygen is 1s2, 2s. Sometimes we just look at the valence orbitals. 2p.
2p4.
2p4, right. And so the electron that's being removed is this one that's paired. And because we're going to get a little extra push, because the two electrons are kind of crowded in one small 2p orbital. If you have two electrons crowded there, there's going to be what we call electron-electron repulsion. Electron-electron repulsion. Versus nitrogen, if we look at the orbitals for nitrogen,
The 1s2, 2s2, 2p3.
here we're just removing a lone electron. So ionizing a single versus ionizing a pair is going to be easier to ionize a pair, so this is why there's this blip here. It's because of electron-electron repulsion, and those are in the 2p orbital. How about the 3p orbital? Would you expect the electron-electron repulsions to be as significant in a larger 3p orbital? No. Yeah, I mean, they're big orbitals, so the electrons can stay further away from each other. So is the blip as significant here? No. And then when you get a 4p, and when we get a 5p, 5p, it doesn't matter, the orbital is so big that the pairing doesn't really impact it. The electrons have plenty of room to stay away from each other. Although, there's a blip here. Anyway, whatever theory we have should be able to fit this, right? But our explanations are kind of ad hoc, after the fact. Ooh, we see there's a blip here, and then try to figure out why there might be a blip there. Okay, but once we're past these two blips, then it goes back to normal. So fluorine's smaller, so it should have a higher ionization energy, and the neon's the smallest. And so it should have the greatest ionization energy in the second period. So, took care of those two blips. Now, the ionization energies here, the easiest species to ionize are the alkali metals. You see all the alkali metals, lithium, sodium, potassium, rubidium, cesium, francium, are all down here. They're all a little under 500 kilojoules per mole. The hardest to ionize are the noble gases. They're all at the top. And so basically, it leads to this. If we're doing anything like redox,
So helium will be the hardest, right? because it's a noble gas.
Yeah, helium's the hardest. If we're trying to react chemicals, then typically we do a redox reaction, let's say for the elements, element plus element redox, or element plus some oxidizing agent or some reducing agent, to get them to react. And so can you tell me what the most reactive elements on the periodic table are? Lithium, sodium, potassium, rubidium, the alkali metals. And the least reactive elements? Yeah, these cost too much energy here to get these to react. These are very reactive. And so 500 kilojoules per mole means extremely reactive. A couple of thousand kilojoules per mole means highly unreactive. And so we put some perspective on that. Well, 500 kilojoules per mole still seems like a lot of energy. Here they're trying to correlate radius with ionization energy. And so you might make a graph of this. See, is there a good correlation? That is, do you get a decent R squared when you try to fit this?
Yeah, what's the ionization energy? No, it's not.
Ionization energy of what?
I was going to look at table 9.4, but
It's about 23, 2400
I was going to ask for specific.
specific number of helium.
I was going to look at the table, but it doesn't seem to be there.
No, it's not there.
I can take that.
It's in the homework.
I can take that.
Yeah, or just ballpark, for right now. So let's test this out. So sodium versus magnesium, which one's smaller? So it has smaller? Magnesium is smaller. So higher ionization energy, correct?
Yeah.
Yes.
The magnesium to aluminum is smaller, but lower ionization energy. Why?
2p.
It's a 2p.
Right.
And then the silicon is smaller, higher ionization energy. To phosphorus is smaller, higher ionization energy. To sulfur is smaller, but
Low ionization.
lower ionization energy because third electron. Chlorine's smaller, higher ionization. Argon's the smallest, the highest ionization energy. So you can see the trend up there. So in the dark blue here, this is what we've been looking at. IE1, the first ionization energy. If you look at the successive ionization energies, we'll see a pattern here. The valence electrons are easier to ionize than core electrons. So sodium only has one valence electron. It's going to cost you about 500. To remove the second electron, which would be a core electron, would cost you almost 10 times. Yeah. Magnesium, the first electron's valence, second electron's valence. So this is going to cost us. But the third electron would be core, and it's going to cost us about 10 times. So between the first and the second, it's about double. Do you see that? But from the valence to the core is about tenfold, just roughly 5-10-fold. Aluminum, 3 valence electrons first, 577. Second is about 2-3 times. Third is about double, whatever. But fourth would be significantly more. And so we can see that the chemistry is going to happen in the valence shell. And with each successive ionization, it's going to cost more and more. So for something like sulfur can lose 6 or gain 2. If sulfur loses 6, how much energy does that cost to completely lose 6? Well, we use Hess's law. If you want sulfur to go plus 6, it's got to be 1,000, 3,000, 6,000, 10,000, 17,000, 25,000, about 25,000 kilojoules. Do you think that's going to happen? No. So what's going to happen is sulfur is going to get in a tug of war. It's not going to completely lose, So oxygen wants to completely take it and make oxide, but it doesn't. So if we make sulfate, then the oxygens are still attached to the sulfur. And here we'll get the +6 oxidation state. The +6 oxidation state, it doesn't mean it's a single ion with +6 charge. It's been stabilized by this. So its actual charge is a little less, otherwise it's going to cost way too much energy. But if you try to take the 7th electron from, look how much energy. That's huge, huge amount. And so one of the things you want to do is you want to kind of get familiar with the energies, like ionization energy, 500, a couple of thousand, and then you look at successive ones. And then the core are huge. Quantity, huge amounts of energy are required.
Do you memorize the first ionization energies?
No.
For,
You don't memorize the first ionization energy, but you should know helium's the highest at about 20. This is 2,500. Just keep it simple. 2,500, and the alkali metals are the lowest at 500. Do you see this pattern here? There are people always looking for patterns. This one made it into Nature magazine. That's pretty impressive.
was it fully recognized? You know?
But we're not going to worry about that pattern. It must be a pretty interesting pattern. Okay, that was the ionization energy. The next one we're going to look at is something called electron affinity. Electron affinity is adding an electron to a gas phase atom. Ionization is removing an electron from a gas phase atom. And so electron affinity is next. Electron affinity and electronegativity. Do you recall what electronegativity is?
How much it wants an electron.
How much it wants an electron. And so, if something has a high electron affinity, it must mean it really wants electrons, right? And so, why do we have two words for it? Why don't we just use one word, electronegativity? You know, that's how much an atom wants an electron. Which one wants an electron the most? Fluorine. Fluorine wants the electron the most. So, you would expect it to have the highest electron affinity, but they aren't the same. Electron affinity and electronegativity are two different things. Electron affinity, the difference is, let me tell you the key difference, is yes, fluorine wants electron the most, but electron affinity combines two things. It combines electronegativity with its ability to accommodate the electron. And so just because something wants or attracts the electron the most, it doesn't necessarily mean it could hold on to it the easiest. And so with these two factors, fluorine should be the highest electron affinity, but it's not. Do you know what has the highest electron affinity? Chlorine has the highest electron affinity. Highest meaning this, it's exothermic. So when fluorine gains an electron, it stabilizes by 328 kilojoules. If you have a mole. And so if we have a mole of fluorine and it gains a mole of electrons, then it's going to go down in 328, become much more stable, much less reactive. However, when chlorine gains, it goes down even further. It goes down to 349 kilojoules, which is a lot more stable in that sense. Relative stability I'm talking about. Fluoride is extremely stable, more stable than chloride overall. But the electron affinities, these are exothermic, so we read these like this. The largest negative number is going to be the highest. Does that make sense? And so the highest electron affinity is chlorine. Why? Well, chlorine has 3 p orbitals. 3 p orbitals are a lot bigger. Fluorine has 2 p orbitals. The 2 p orbitals are a lot smaller, so the electrons are going to be much more cramped in a 2 p orbital than a 3 p orbital. And so chlorine doesn't have quite the ability to attract it, but it has great ability to accommodate. Fluorine can attract it, but it's going to be cramped. And when it's cramped, we have electron-electron repulsions, which lead to destabilization. Now, if we have a positive electron affinity, that means it does not want an electron. That means it's going up in energy, which is becoming less stable. We want things to go down in energy to become more stable.
Is it potential?
Mm-hmm. This is all potential energy, delta H. And so when we look at this is all at 25 degrees C. Which brings up the other question. This is always a trick question, and that is, what are standard thermodynamic conditions?
25 degrees Celsius at 1 bar.
There's no standard temperature in thermodynamics.
Agreed upon the same temperature.
So we can't assume this is at 25 degrees C. You know the little superscript 0 here?
Yeah.
The little superscript 0 means under standard conditions. This should be under standard conditions. Standard conditions means the gases are at 1 bar, 1 atmosphere. And if I'm dealing with an aqueous solution, this is gaseous. If I'm dealing with an aqueous solution, the aqueous solution should be at 1 molar. Or in the U.S., we use this. These are for standard thermodynamic conditions. So you see the little superscript 0 there on the E?
Yeah.
That means standard conditions, which means no more ion concentrations of gases at 1 atmosphere for this chart. The reason why there's no standard temperature is because people don't want to be fixed. Some reactions you have to do at elevated temperature. And if that's the case, then we don't want it. We don't want to fix the temperature. But then that starts to become inconvenient. And so most people will just do 25. But that wasn't worth much. So if you put 25, if you put 0, I mean, it wasn't worth much because you're going to get partial.
Are you saying if we put 25 degrees Celsius, we got it wrong?
25 degrees Celsius is wrong.
No.
But did you put other stuff on there? Or only
Absolutely.
Yeah. Okay.
I put 25 degrees Celsius at 1 molar at 1 atmosphere bar.
Okay. You're fine.
I didn't know that temperature could be non-fixed.
Only the temperature. So when you see this, you're restricted. You're restricted to what? This is what makes thermodynamics hard. So for example, if you were to use this and the pressure were 0.5 atmospheres, that's totally wrong. Right? If you were to use this, the pressure's got to be 1. And if pressure's not 1, then you can't use it. And so you have to keep track of all these things in thermodynamics, which makes it a big pain because it's hard enough just keeping track of one thing, and then to have to keep track of so many different things. This is why so many people fail out of thermodynamics and have to repeat it. I think in my class, well, I was close to being one of those that failed out of thermodynamics because I didn't keep track of any of this stuff. I didn't care about any of this stuff. Just give me a delta H, I'll do the calculation. Standard? No, you just use the same equation for everything. Use the same equation for everything, and that leads to the problem. Well, fortunately, I didn't have to repeat it, but a lot of my students in my thermo class ended up having to repeat the class. They're all chem majors. Well, anyway, so we have electron affinity here. What do you think has the highest electron affinities? What do you think have the lowest electron affinities? So now they flipped it. And so do you see they added a negative sign here? And so rather than going down, into a well of stability, they're going up. I don't like to flip my thinking. I'd like to just keep it the same. So if I'm looking at going into a lower energy well, I like that. And so what has the highest electron affinity? They want higher to be a big positive number. So They ended up changing it with a negative, but in the table, it's not going to be like this. You know? The highest electron affinity will be fluorine or chlorine? Chlorine. And the lowest electron affinity will be the noble gases. They're so low that they're going down here. But for the rest of them, these. Now, some of these are exothermic, so why don't we form like a sodium ion? We could, you know. For example, if we form a sodium ion, it becomes more stable. Yeah. It does have, in this case, a positive electron affinity. We want positive. When we actually look at the electron affinity for sodium, it's minus 52.9. So it is possible to form a sodium ion. You know, forming a sodium ion seems to be more stable. Well, yeah, sodium positive, but what about a sodium negative? What would we call this? Sodiumide ion, maybe, or, you know, sodium comes from, yeah, natride, natrium, natride, something like that. Yeah, so it could, but, you know, it's not that great. But it just shows that all of these have favorable electron affinities. The most favorable would be chlorine.
Would the less favorable then be like anything that has the greater than 0 sign?
Yeah.
If that's the case, why does nitrogen, the only thing with +7, would it also have just a greater than 0?
No, nitrogen you would expect to be less than 7. But can you tell me why that nitrogen's kind of weird? Phosphorus is kind of weird. Arsenic's kind of weird. Antimony's kind of weird. They're all kind of weird because the smaller the size, the higher the electronegativity and the higher the electron affinity, except for the noble gases. Noble gases are very small, but there's no place to accommodate them unless they go in the next higher energy cell, which would be terribly unstable. But these ones are weird. These ones, you see there's something going on there. What?
They have a half-filled shell, which is stable.
They have a half-filled shell, which is stable, but it's not because, we wouldn't call it because of that. What we call it is because of this. That electron would go into a half-filled shell, which would result in electron-electron repulsions.
So
That's why nitrogen is +7. It's got small orbitals, and then you're going to get more electron-electron repulsion because the electrons are going to be too crowded in the 2p orbital.
I'm just curious why that's the only listed positive.
The other weird thing are these. Look at this. Beryllium and magnesium are positive too. Why is that? It's not because of electron-electron repulsion. It's because of jumping into the 2p, because the 2s are already filled here. So the extra electron has to jump up to the 2p, which is higher in energy. And so we see similar kinds of weird things happening here that we can understand based on electron-electron repulsions, or jumping from one subshell, the S subshell, to the P subshell. Similar kinds of blips there. The numbers we don't really pay too much attention to here. Ionization energies we pay more attention to, but still this is good. And we have the same thing. This is called EA1. Some things want 1 electron. Fluorine, chlorine, bromine, iodine, those want 1 electron, but some things want 2 electrons. So oxygen, for example, wants 2. Oxygen wants 2 electrons, so we have EA1 that's favorable. 141 kilojoules favorable. But we have to add another electron to it, and that's called EA2. And then we have to use Hess's law to combine EA1 and EA2 to figure out how much energy is involved in giving oxygen 2 electrons. The same thing with nitrogen. Nitrogen would have EA1, EA2, and EA3 that would have to be combined.
Would their EAs be similar to that?
Well, the EAs become less and less favorable. EA1 is the most favorable. Now let's take a look at EA2 for oxygen. EA1 is very favorable. Do you see it's going down in energy? But what's happening with EA2? It's gaining energy. And in fact, it's gaining a lot of energy. So overall,
Does oxygen really want 2 electrons? Oh. No, how much energy is that going to cost? If oxygen gains 2 electrons, it's going to cost you 600 kilojoules. 600 kilojoules is a lot of energy.
It's just saying a lot.
Yeah, that's a lot of energy. That high, look at what they say. The high positive value of EA2 makes the formation of gaseous O2 minus seem very unlikely. That's a lot of energy. The ion O2 minus can exist.
That's like a superoxide.
Why? Why? Well, no, oxide. Remember, oxide wants to be -2. Chloride wants to be -1. Chloride, it makes total sense. You know, chloride wants to be -1 because it's going to be more stable. But why would oxide want to be -2? It seems like it would be more favorable to be -1. In other words, the energies don't add up. Energies don't add up according to, remember, our octet rule and all that stuff. It doesn't quite follow that. There's a mismatch here. A mismatch is, remember we were thinking that they want to gain electrons to be like the nearest noble gas, or they want to lose electrons. Everything's costing energy, and it's going to cost a lot. So, for example, magnesium, or actually, let's do aluminum. Let's figure out how much energy this all costs. So, if we do aluminum, we go IE1, IE2, IE3. And this takes us to aluminum ion. That's where we want to go. So let's just ballpark how much energy that's going to cost us. By going back to the chart, ionization energies here. So this is about 600 plus 1800 is going to be 2400, about 5,000. This is about 5,000 kilojoules per mole. Plus 5,000 kilojoules per mole. Let's take a look at oxygen. We're going to have EA1. Is the oxygen -1, which would be like peroxide. And then we have EA2. Peroxide seems like it'd be very favorable to form, but peroxides are terribly unstable. And then we have EA2, which would take us to oxide. How much energy is that going to cost us? About 600 kilojoules per mole, positive. So if we're going to form aluminum oxide is Al2O3. We need to double this, so that's going to be about 10,000 kilojoules. And we need to triple this, which would be about 1,800 kilojoules. So altogether, it's going to be about 12,000 kilojoules. 12,000 kilojoules, is that going to even happen?
Most likely not.
It just doesn't seem right because we got to form 2 Al pluses and 3 oxides. 12,000 kilo. How much is it to get helium to react? 2,500 kilojoules. And helium is what we call an inert gas, noble gas. Helium doesn't react with anything, so why would this react? It's going to cost us way more energy than getting helium or neon. Neon's a noble gas too. It's going to cost us way more energy. I thought metals wanted to lose electrons and non-metals wanted to gain electrons. If metals wanted to lose electrons, then why is it going to cost money? Shouldn't you get it for free? It's so much. And so, can somebody explain it to me? Just because people think, oh, it's more stable. You know, having a completed octet is more stable. Yeah, oxygen has a completed octet, but at what cost?
I think that has to
do something with what it's bonded with. Like O2 minus is not going to exist
Right.
like alone. So maybe it would cost that many kilojoules just to make oxide
Yeah.
bonded.
Right. Right, exactly. That's the reason why.
Because we're forming gas phase ions here. What happens is these come together and they're going to be very attracted to one another. +3 and a -2, you're going to form extremely strong bonds. Which one would be the aluminum? Which one would be the oxide?
The little one is
The little one is oxide?
no little one.
The little one's aluminum. And the big one's oxide. And what happens is when we form the ionic bonds, we get huge amount of energy back. And this becomes extremely stable. Yeah, we're going to form an ionic lattice. The formation of the ionic lattice can easily pay for that because of the bonds. We're going to look at the lattice, what we call the lattice energies, but we're going to lose more than 12,000 kilojoules in energy. And so losing that, it can easily pay for this. And so what makes favorable ionic bonds? Well, favorable ionic bonds, why didn't we stop here? We didn't stop here because this is a -1. It's going to be a weaker ionic bond, right? And so we go to -2. -2 should have twice the bond strength than a -1. But if a -2 has twice the bond strength, why don't we go to -3? We should go to -3 because -3 should have triple the bond strength, right?
Right.
In fact, why stop at -3? Why not go to -4? Because -4 would have quadruple the bond strength. Well, actually, I might as well take it to minus like infinity. If we go to minus infinity, then
We'll have infinite bonds.
yeah, infinite bond strength.
Hey, it would never break
so-
at all.
But we can't even get to -3. Why? Because the electron would have to go in the next shell. Going into the next shell is going to cost a heck of a lot more energy, like 10-fold more energy. And so it's got to stop here. Does that make sense?
Yeah.
And so it's always going to go to the max it can go because that's going to create the strongest bonds. And so the thing with aluminum is we don't stop here at aluminum +1 because we can get twice as strong bonds with aluminum +2, but we can get 3 times as strong bonds with aluminum +3. But we don't go to aluminum +4. Why? Aluminum +4 is not going to happen because we'd have to be ionizing core electrons, which is going to cost us 10 times. And then the payoff's not there. And so the payoff is going to be with the valence electrons in the valence shell. And then we're going to try to max. This is why we either, like for example, chlorine, we're either going to gain 1 or lose 7. It's all happening in the valence shell. And so we're going to try to get the maximum charges with the minimum cost. And that's going to be with the valence. And even though these are all endothermic, overall it's going to be exothermic because when we form those bonds, it leads to great stability. Oxide is terribly unstable in alone. And so this is why they say that it's unlikely. Of course it's unlikely. It's a O2 minus in the gas phase. It's going to be super reactive. But it's very likely it's going to form if we can form ionic lattice like rust or whatever else. All right, the next thing we're going to look at quickly are magnetic properties. When we have unpaired electrons, we call it paramagnetic. And so the D subshell here is paramagnetic, and we're going to have 5 unpaired electrons, and we can measure how many unpaired electrons it is by how magnetic it is. When everything's paired, we call it diamagnetic. Diamagnetic materials are weakly repelled by magnetic fields. Paramagnetic materials are strongly attracted to magnetic fields. So diamagnetic, weakly repelled. Paramagnetic are attracted to magnets, and the more unpaired electrons, the stronger the attraction. So this is paramagnetic, this is paramagnetic here. This is paramagnetic here. You can measure the difference because here we have 4 unpaired electrons, 5 unpaired electrons. Here you can't really tell the difference. There's one other thing called ferromagnetism. Ferromagnetism is how these magnetic domains can interact. We'll talk about ferromagnetism later. Okay, there's something called polarizability. Polarizability is a cloud. If you have a big fluffy cloud, we call it polarizable. If you have a hard small cloud, then we don't call it polarizable. Its polarizability is quite small. And so the bigger, the fluffier the cloud, the more polarizable it is. And that is, the easier it is to distort the cloud here. And so here we have our electron cloud, the 1s orbital here. So like a 5s orbital would be highly polarizable, it's just big, versus a 1s orbital, which would be a lot less polarizable because it's small. And so it just causes distortions in the cloud. And the cloud was negative charge density when we look at the cloud. So the polarizability of an atom increases with the size because you've got bigger orbitals.
There's cesium all the way at the top.
Yeah, cesium is very polarizable. So what are we going to do with polarizability? We're going to talk about polarizability later. Do you guys remember London forces? Yeah. Instantaneous dipole, induced dipole? Yeah, instantaneous dipoles are much easier to make on polarizable materials. We'll talk more about polarizabilities later. Here, this is just showing size and polarizability. The bigger the size, the easier it is to polarize. Here's a summary. We talked about ionization energies, we talked about atomic radius, we talked about electron affinity. Electron affinity is not mapped out here. These are the periodic trends. There's one more periodic trend here. Do you know what the most metallic element on the periodic table is? Cesium. Cesium or francium. Cesium, metals tend to lose electrons. Well, cesium loses electrons the easiest. Right? Metals have other properties too, malleability, ductility, et cetera, et cetera. So those are going to be here. Electrical conductivity, the best electrical conductivity. As we go up and right, the elements become less metallic, more non-metallic. And so there's a trend as we go left to right. We start off with metals on the left. We go through semi-metals over here, kind of in the middle, and then we go to non-metals on the right. Non-metals tend to gain electrons. Non-metals are harder to define. Metals are easier to define. But, the most important ones were ionization energy and whatnot.
What about metalloids? Are those easy to ionize?
Metalloids are in the middle. So metalloids can go either way. So, for example, carbon can go either way. It can gain or it can lose, and it's kind of stuck in the middle, so it doesn't really matter which way it goes. Chlorine would much rather gain than lose, and sodium would much rather lose than gain. So metalloids are kind of in the center.
Carbon can either be methane or CO2.
Right, exactly. So that's the situation with that. We're in chapter 11.
What about chapter 10? We're still in chapter 10?
No. We're not skipping chapter 10. I accidentally skipped it.
So you just finished chapter 9. Just kidding, sir.
Oh, I've already started talking about chapter 10. Do you know what these are called?
Pure generated electrostatic potential map.
If you take all the orbitals and just map it out, this is the electron cloud kind of for the molecule, basically. And the electron cloud isn't homogeneous. When we look at the electron cloud kind of thing, we have red regions, green regions, and blue regions. Now, what do you think? The electron cloud is going to be more negative in certain places and more positive in other places. And so this isn't an orbital here. This is just kind of mapping out. This is called an electrostatic potential map. And so it's mapping out the positive and negative and neutral regions of the molecule. So if you were the first person to assign the colors, what would you assign? Would you assign red as positive or would you assign red as negative?
That is positive.
I would assign red as positive because I think batteries, But this person,
They did negative.
they assigned red as negative and blue is positive. So I always have to remember it's backwards from what I would have assigned. And so this is negative, this is positive, and green is neutral. And so this is very important because chemistry is all electrical interaction. So this tells us how the molecule is going to interact with other things. And so we want to know different parts of the molecule. And so acids are positive or acids are negative? Acids.
Acids are positive.
Acids are positive. Bases are negative. And so if I'm an acid, I'm looking for blue or I'm looking for red? If I'm an acid, I'm looking for red. If I'm a base, I'm looking for blue.
If you're water, you're looking for
If I'm an oxidizer, I'm looking for
blue.
blue. Yeah. If I'm an oxidizer, I'm looking for blue. If I'm a reducer, I'd be looking for red. This is, over here we have ethanol and methanol. Ethanol and methanol. And these are computer-generated electrostatic potential maps. This is, if you spend, what was it, $25 or $50? I have the, I have the iPhone version of, what was that program called? The quantum mechanical program?
Is it the one that you wish that was on the computer?
Yeah, the one that I wanted
like
on the computer. They didn't have the budget. After COVID, we had it. We had it on all the computers, and after COVID, nobody was using it during COVID. The computers wasted like $10,000, $12,000. After that, they weren't spending any more money on it. But we can generate this using Spartan. The student version of Spartan is cheap. Also, there are other deals that undergrads can get. One is like a membership to the American Chemical Society. You can get that super cheap too.
Like a free access program. Better yet, do it yourself.
Yeah. So what we want to do is we want to do this without spending money. Can you draw an electrostatic potential map, or just kind of do an electrostatic potential map without spending any money?
Yeah.
Yes, we can do that.
You can do it by hand.
So we can do it by hand, and we're going to save lots of money. But do you think ours are going to be very accurate?
No.
Not really.
No, but maybe it's good enough. Because all we're looking at is where the base wants to attack and where the acid wants to attack most of the time. Most of the time we're using these, that's what we're looking at. And so if you're a base or if you're an acid, then and there's ethanol around, then those are potential sites of reactivity. So, to do this with the low budget, are we going to have a fancy three-dimensional drawing like that?
No.
Or that's a three-dimensional. What we're going to have is a crude. Well, we're going to start off with a crude
Drawing?
Lewis structure. And so here, Lewis symbols, we talk about that. Lewis symbols can tell us about reactivity here too. With Lewis symbols and Lewis structures, we only look at the valence. So we start ignoring the core, and we only look at the valence. So yesterday I asked you to draw the orbital energy level diagrams. Most of the orbital energy level diagrams that they write for these types of things just show the valence, and they completely ignore the core. And you wouldn't do it. And so here, chlorine has 7 valence electrons. It wants 8. Does it really want 8? Yes, chlorine really does want 8 because that's the most, or the highest, what do we call it? Chlorine has the highest electron affinity. And in fact, that electron affinity is 350 kilojoules. we're going to go 350 kilojoules down in energy in this well, nice low energy well. You know, that's where you want, if you're afraid of heights, that's where you want to be. You want to be down in the lower energy well. However, sodium is going to go up. You know, how much energy does it cost to ionize sodium?
52.
Not 52, just ballpark.
Weirdly do.
So we're down 350 kilojoules in this nice low energy well, but sodium is going to do what? Sodium is going to go up 500 kilojoules. Remember, sodium is about 500 kilojoules. So what's sodium doing way up there as sodium ion? You know, because we got to ionize it from sodium to sodium plus. That's going to cost us 500 kilojoules. And the chlorine's down here at 350 kilojoules, and sodium's up here at 500 kilojoules. Average, it's going to be, well, we got to add it up because it's Hess's law. So 500 minus 350 is 150. So we're going to be 150. And so we're no longer in this nice, we're 150 feet up on top of the well. That's not very stable. And so, but what's going to happen? We're going to form an ionic bond. When you do Lewis structures, how do you draw an ionic bond in Lewis structures?
Brackets with a charge.
This is an ionic bond drawn. What? Should we draw a line there? So should there be a line connecting sodium and chlorine? If I ask you to draw the Lewis structure for sodium chloride, I don't want to see this. Although I see this all the time. When I ask people to draw the Lewis structure for sodium chloride, they draw this. That's not it. The Lewis structure for sodium chloride is this. And if we want to get extra fancy, we could draw the lattice, you know, or try to draw the lattice, which would be something like this. And so we don't show ionic bonds with lines, right?
It will be like the reverse, right? Or is
No, lattice is not reverse. Lattice is just stacking it on top and building bigger, bigger, bigger crystals. How do you build a bigger crystal? You just add more.
so it's diagonal.
But anyway, this would be the lattice, the start of the lattice. You know, this would be a baby crystal, and then to build a bigger crystal, you just keep adding it. And so we try to manipulate baby crystals to make bigger. Whereas in HCl, we're going to show covalent bond, but we don't show it by two dots or a dot and an X. We show a line there. So HCl fine, NaCl not fine. These are two Lewis structures that we do here. And so I'll talk a little bit more about Lewis structures for ionic, but you guys are familiar with Lewis structures for molecular, right? This Chem 4 type stuff. All right, so we're out of time.
Just to confirm, the oxidizes and acids want and then the reduces and bases